Okay, cool. We're recording. I will share that window. There we go. Cool. So can everyone see my browser window?
Yes.
Yes.
Okay, great. Cool. So I'm gonna I guess I'll present out of this doc, and then we may walk through VS Code kind of towards the end when I start looking at the implementation of it. But I figure this will be a good place to start. So what I'm hoping to cover is kind of in this outline section today so basically talking about denstar and async functions and traits or in dyne traits in trait objects and talking about all the things that sort of is going into making that work. So we'll talk about one, like kind of what's the problem? Why is it hard? Like Michael did a lot of work to make async functions work in static traits and talked about that at the last one of these sessions. And so what's missing then to make, like, why doesn't that just apply to dyne traits directly? So we'll talk about that. I'll give kind of an introduction of what this new denstar thing is that we are working on. And then talk about how that enables async functions and dyne traits. And then I'll spend some time talking about the implementation and what's next in it. So yeah, feel free at any time if you have questions, either to drop them in the doc or just like unmute and talk to me and tell me, and we can go through this. So excuse me. So first of all, why is this hard? And basically, so I have like kind of the one sentence summary there, but I'm going to elaborate on it with some code examples. And so we don't really know the size. Really, we don't know the type of the future that I should say type rather than size here. Size is kind of the relevant thing because you need to know how much storage to allocate for the type that's going to get returned by these async methods. But yeah, the type's the real thing. So let's make just kind of a quick example. So let's have a trait. I'm going to call it reader. It has a function that's like, read data, which takes self and a buffer, which will be like whoops. There we go. And I'll also have it be like I'll have it return a U size for how many bytes was written. So this is kind of a fake reader trait that we'll use as an example. And so I can make like a null reader struct that doesn't have anything in it, and then I can do impl reader for null reader. And then so we have read data. I'll just copy it from up here. And then this one is just going to be sort of so we'll make buffer be ignored, and we're just going to do return 0 and just kind of do nothing in there. Whereas like I can also have a like file reader. Oops. That I don't know, has a file in it. And so for this I can impl reader for it. And like oops. So let's say for some reason it doesn't really make sense to do this, but like let's put a temporary buffer in there. And that's going to be like 0u8 and then it's like a 1k buffer, we'll say. So then I can do like self.0.read into like that. Let me make that mute. Oh, and then we'll do .await. So we have a suspend point in there. And then let's say like, copy. I'm just going to omit the rest of the details here. So we'll like copy into. And then like we'll return, I don't know, temp buffer.len. So this is like almost certainly wrong, but the points here just kind of show what kind of some of the issues that we might run into. So if we remember from if you had the chance to see Michael's talk last time, or if you just know this, we know that like these async functions end up being like sugar for an associated type that gets added to the things, or added to these the traits in the impulse. So what this kind of I'll just make a copy of this whole thing. So so the compiler sort of generates this where we'll have like a type read which impulse future output. There's some lifetime stuff that goes on here too, but I'm just going to ignore that. And then this turns into like fn, and then this return basically returns read data. That has to be something like that. And then so each one of these is going to have a different like thing. So here it's read data, future is like yeah, so this will be so this will have some like async block that returns 0. And then so this is going to be like I need a good bracket that's like not actually in Rust, but I think we use all of the easy to type ones. So I'll just say this is type the type of the async block. And okay, so this async block makes it's like a concrete type, but you can't name it right now. And then if I do the same thing down here, then so we have fn like that, and then we wrap the whole inside in an async block. Each of these async blocks has a different type. So anyway, that's kind of a review of async functions and traits for the static case. But let's look at like what happens when we do this with dynamic traits. Or trait objects. So let's say I have like async fn. There we go. Let's say process data. And then we want to take a or I'll call it reader, and it'll be a dyne reader like that. So what we want to do is, and then we can call it with like, so we'd have like, let's see. And we call like process data like that. And then we can do the same thing with like, with file also, with my file reader. And then I'll just say there's this open file function that I'm not going to bother defining. And then we do the same thing. So we call read data. So then we'll say like let future, or like, yeah, I'll just call it future. And we can say reader dot read data. Oh yeah, we need a buffer also. Oops. Okay, so we have this future, and then we do like future dot await, and then we, I don't know, do stuff with buffer. Okay. So normally you just write this as like read data dot await, like you don't really save the feature into a local variable. But the reason I wanted to call it out here is because this has some type. Whoops. And the problem is like so this is stored right now, the way we've written this is stored on the stack. And so we need to know how much stack space to allocate for it. And if we did like the null reader, we don't really need any stack space on that for all or at all, because it's just returning a constant. Whereas if we do this like other one that I made where I've got this temporary buffer in there, we need to like reserve a kilobyte of space in addition to the kilobyte for the buffer that we already had. And the problem is from just the signature of like this Dyn reader, we don't know, that doesn't tell us enough information to know what to do there. And so that's why this doesn't work. So there's some workarounds to it. So we can box the return types. And so what this ends up looking like is we would just, so if I do my reader trait, rather than writing like async function whatever, I'd write like fn read data buffer takes a mute u8, and then we'd return like I think I guess I'll just do box of like that. Anyway, so this works because we now like we know it's a box, it's a or actually no, it's not impl feature there, because then we'd run into the same problem. So it's a box Dyn feature. So this works, like we know we have some Dyn feature and it's stored in a box, and so because of that we just need a pointer to it, and so we can allocate space, or we can keep all of our stack space that we need to hold the box, or like the pointer to the box. And that's okay. But then it's also kind of not great because we have like allocation that happens, and like in some environments you can't do that. If you're in like a no-std environment, you can't allocate any data for the box, or like we just don't have an allocator, so you can't do this approach like generally. So we want something that works in there. I guess another way you can do it is like be explicit about the return types. Let me put like a heading on that. And this doesn't completely work, but it, excuse me, sort of works. So here, let me take our process data function and copy it down here. If you remember, we sort of like desugar this into we resugar or desugar these like functions into like associated types. So we could say we can specify something about the type of the associated type here. So we can say like where read has, I guess it would be equals, and we put some type here, and then here this is just the feature is like reader, or I guess it'd be like
Could it be a type parameter of your function?
Yeah, I'm trying to use like the sort of fake syntax, or the proposed syntax for named function return types, but it's not really real syntax, so I'm kind of making it up as we go. So it'd be like reader is reader, read file. Whoops. So then this sort of works because we can put in the signature what type we want. But then it still doesn't really work because it requires that anything we pass into this process data function uses the same type for that feature. And so we could say, oh, okay, you can do it with like null reader, or you can do it with the file reader. But you can't, this wouldn't work for both of them. So we need some way that's like, that gives us a concrete type that can still like sort of hide all the details about what's in there. So the box is closest to what we want, but we want to be like kind of generic around pointers. So I think I guess I should ask any questions so far. Does this make sense? Sounds like either yes, it makes sense, or everyone's too confused to ask questions. So either way, I'm going to move on. So now let's get into like what is Dyn-Star. And so this came out of this question that I guess Nico and some other people were meeting with Josh Triplett talking about async functions and Dyn traits, and I think it was Josh that had this observation of like, what if we could make Dyn trait sized? So right now we have these types like Dyn trait, and this is I guess I can write it like what's being sized like that. So we don't know the size of a Dyn trait type. And so because of that, you never really see Dyn trait just by itself. You always see it as like box of Dyn trait, or like you can have a reference to a Dyn trait, or like or you can do like arc of and so on. So basically all of these types that I've put there are like pointer types, either built into the language or provided by the library. And that's how you end up always manipulating a Dyn trait. And in a way, what we did in this example up here with this box, or returning a box, so we just sort of picked one. We said, here's the allocation strategy that you have to use. And we could have put anything there. Like we could have put like a mute Dyn, or like a ref mute Dyn trait in there. But if we do that, then we have questions about library or lifetimes, like where does this thing get allocated from and live and all that, and that ends up being hard. So the idea of Dyn-Star, at least the way I think of it, is to kind of like abstract out over all of these things. So representationally, the same way that like anytime you have a pointer to a Dyn trait object, that gets represented as a fat pointer. So like we have a Dyn trait is a I'll call it a wide pointer, I guess. So which has like a pointer to the actual, and then it has a pointer to a v table. So it's basically this data v table pair. So the idea is to basically do the same thing. So like Dyn-Star trait is also 2 words. And this will be something and a pointer to a v table. And so the cool thing is that this can be a lot of different things. Like we can put basically anything we want that fits into a pointer size value, we can put there. So we can have like, that could be like a box of T and like a v table. Oops. Or it can be like and or anything else in there. But the key difference is that the v table, so v tables include a drop function in it. They include drop glue. So the key differences here is that the drop glue or the drop function that's in the v table will take care of doing anything that needs to be done to free the underlying thing. So in the case of a box, it drops the box and frees the box. In the case of like a shared pointer, it doesn't do anything. Because those are just pointers, you don't really have to do anything for drop glue on those. If it's a reference counted pointer, then it drops or like decrements the ref count, and if it's 0, it frees it. Then and so on. But then what this lets you do is you don't have to, like I can do to pull back our like running example again. I can have this take a Dyn reader. Well, actually, no. What we'd probably do is leave this the same, but this gives me something that I can put in here where I can now say this returns a Dyn future with output equal to usize. I think is what we've been doing for that. And then basically we can now this works with a whole bunch of different things, and it doesn't necessarily like require allocation. And so so we still or yeah, anyway, so that's what Dyn does. And I guess now we can get into how it enables async functions and Dyn traits. So is there any questions so far? Any questions? Okay, I'm seeing shaking heads and thumbs up, so we can go on. So the idea here is like whoops. So if we have our let me scroll back up and grab the version of this that I want. Whoops. So as it is, this trait like isn't Dyn safe because you don't know what the type parameters are going to be. But what we can do is we can say something like, okay, I think this is going to be kind of horrible, but it's I think morally like what's happening here. So we can do like Dyn safe reader, which so this read data feature would be or wait. Actually, I think all it ends up being is a Dyn safe reader extends reader with read data feature equal to Dyn of like that. So now when I write my process data function here, I can take just the regular like Dyn safe reader that, and it just kind of works. So we know we're going to get a Dyn out of it. But we need to have kind of like some way of doing an adapter between these, because my up here, my null reader thing, for example, it returns some opaque future type. It doesn't return a Dyn so we want to have some way to like convert that into a Dyn so we could write like an impl here. We can say like impl Dyn safe reader for T, where T impls reader. Oops. And so basically this ends up doing sorry, my computer wants me to do something with printers. I don't know why. Anyway, so what we can do now is basically say like so this is going to return a Dyn future output equals whatever. Sorry, that's usize. So we can do like self as reader. Hopefully the syntax here is basically so this gives us some kind of like let inner future equal that. And we can just return, in this case, I'm doing the box. So we'll assume we have boxing available. And then, anyway, so yeah, so then we can coerce this box into a DIN* feature. From outside, you don't know it's a box. Like I could also, if somehow, I could imagine like having a static reference that I return instead. So like I could have some other one that's like, impl. I guess like for null reader, I could probably do this. Where we could just return like, let's see, what would it be like? I think just like that, as long as that's a constant and it turns into static. I'll add a comment to say what I'm trying to do here. Okay. So if we have something like this, basically anyone who's calling it, they just know it's a DIN* thing. They have a pointer with some data to it, and they have a vtable. The vtable knows how to free any memory that needs freed up, and everything's happy. So that's the way DIN* helps out with this. But there's sort of more needed, because there's a lot of boilerplate that I've ended up writing here. So I think these are kind of like open questions. But basically there's still a lot of boilerplate. How much can we? So this might mean adding some new features or adding macros or something like that. One of the ones we've talked about, I don't know if we're still planning to do exactly this. I think we got kind of mixed reception when we floated this idea before. But the idea is to have some sort of boxing built-in type that wraps like a trait and basically makes it box all of the return values from or all the return features for it. And then that would make it so you can just say like to change something into a DIN* or like to a DIN trait that's DIN safe. You would just put like wrap it with boxing, and that would make it like automatically box all the return values. But I don't know if that's what we're going to end up going with or not. That takes some kind of fun compiler magic, because right now we don't really have a way to make like impls that are generic over all trait impls. Like you can't say like, if I have a box of T, here's how to implement every trait that T implements on that box of T, which is kind of what we would want to be able to do this generically or without any like special language features. So anyway, does that make sense so far? Any questions? Okay, seems like not. Okay, so we can walk through some of the implementation, and I think for this, it's probably better if I share a VS Code window. So I'm going to do that real quick. Let's see. Say new share. I want to do my whole screen. I just want to do VS Code. Here's that. Here it is. Okay. Can everyone see my VS Code window? Okay. Is the font size good? I'm on kind of a big monitor and I have a size that makes sense for me, but okay, cool. Seems like people are okay with it. Okay, so in the notes, and I think, yeah, I did post the notes, the link to the notes in the Zulip. I had kind of highlighted a couple of like,
someone is
I think,
asking to zoom in.
Sorry, what?
Oh yeah, someone in the chat was asking if you could zoom in.
Oh, okay. Yeah, I will. How's that? So let me just get rid of my console. Oh, there's the chat. Okay, I haven't been able to. Okay, great, cool. Yeah, good. I'm glad it's working. Okay, so I highlighted kind of a couple of key points. There's a lot of so the first thing I did is I linked to the PR that has a lot of like the baseline implementation of it. That code changed actually kind of significantly in parts since that initial PR. But the kind of rough outline of that's there. So if you want to see how this whole feature is implemented, that's a good starting point. I pulled out a few points out of there that I'll highlight for this. And then there's also just kind of a lot of like plumbing different things through a lot of other code too. So anyway, let's go through that. So first there's here. So to parse this, so basically the dinstar. Oh, something I meant to say in the intro to dinstar section that I should make sure to say this like loudly. Dinstar, we're not planning on that ever being user-facing syntax. Like we're implementing it now with syntax that you can write and use and all that, but it's really this is meant to be an implementation detail of supporting like async dyne trade objects. So we're not. There may be some way to get to there in the future, but that's not really what we're looking at right now. This is so dinestar it's best to think of that as like placeholder syntax. That said, to write tests and things, it helps if you can write code in with that syntax. So we add some parsing. The parsing is really easy. We basically, when you start parsing a dyne type, so here we read the dyne token. The next thing we do is we check if the next token is a star. And then if it does, we say it's a dyne star trade object instead of just a regular like dyne trade object. And then that syntax gets passed into the trade object. And then basically we plumb this through the AST. So that's, parsing is pretty straightforward for this, but that's also kind of the starting point because now we've updated this like trade object type kind with this trade object syntax. And then that ends up, the great thing about having a strong type system is that when you make a change like this, you get a lot of type errors. And so that tells you kind of all the places that you need to change to make this work. So anyway, that's parsing. And then for type checking, this is done as a coercion. So yeah, so we have this function coerce dyne star, which is basically responsible for doing this. So I'll try and walk through what's going on in there. And this code's changed a little bit since the last time I looked at it, but yeah, we can still go through it. So the first thing we do is look at whether we're casting from a dyne star to a dyne star. And then if we are, and they're the same, that's what this line's checking whether so the principal def ID, that's basically the main, like it's a, dyne star foo, the principal of def ID will be the foo part of that. So if they're the same, then we just say, okay, great, we can do it. We just say, as long as these things unify, that's fine. If they're not the same, then what we're doing is sort of a trait, like an upcast. So it's, we have a foo and a bar, and like bar extends trait foo. Can you cast a dyne star bar to a foo, and that's an experimental feature right now. So if we don't support it, or if we don't support it, we go ahead and error out here. Otherwise, I guess we continue. And then the upcasting gets handled kind of just automatically through the rest of this. And so basically the rule that we want to, what we want to guarantee, we want to check that, like, if you're doing, say, like X as dyne star foo, we need to have, we need to say like X impulse foo. This is kind of like the main thing to check. And so that's what this is doing here. So we're walking through, any of the thing from the, let's see, where does predicates come from? Oh yeah, predicates, I guess, gets passed in that way. But we're walking through all of the, like, things that we have on the dyne star thing that we're casting into, and then making sure that those all hold with on the type that we're casting into it. And that's basically That's basically all we need to do well, there's more we need to do, but for now we're just saying, hey, if you can cast anything that implements a trait into a Dyne star of that trait. The thing that's missing is we need to have size restraints on it. So we like reserve a pointer sized field in the Dyne star object, and that's where the object has to go. And so Michael has a PR out for that now that adds that check. So then that there's sort of two things. We want to make sure that the thing we're casting into the Dyne star is pointer sized and that it implements the trait that we expect. So that part's pretty simple. And then basically I forgot where this happens, but we then have a part that says like Dyne star trait, impulse trait, and then that kind of feeds through the rest of the trait solving logic. So that's basically type checking. Good so far? Makes sense? Cool. Okay, so the next thing I want to look at is layout, and layout's pretty simple, but it's still kind of worth pointing out.
There was a quick question in the chat.
Oh, sorry. Yeah, I'm bad at not seeing the. Oh, can this be smaller than pointer sized? That is a good question. I expect what'll happen now is it'll ice. But yeah, I think in the future we'll support it. Cool, thanks. Yeah, I don't think there's anything fundamental that says that it has to be exactly pointer sized. We could make it smaller, but I think right now to keep it simple, we're just making everything be pointer sized. Cool. Okay. So then the next thing is layout, which is here. So okay, I think I was like, oh no, what is going on here? Basically what the layout is doing is we're just saying that, hey, if you have a Dyne star foo, it's a thing that takes two words, so like two U sizes. And basically the way this code gets called is it asks like, what's the layout for a given field? So we treat our Dyne star as like basically a tuple with two fields in it. So if we're checking the 0th field, that's just the U size because we put any kind of U size data that we want in there. And then if we're checking field 1, that's where the V table goes. And I bet this code is, where is it from? I guess this comes from somewhere else, but I think basically we're just saying, hey, it's an immutable reference to an array of 3 U sizes, which I think is just kind of a proxy for a V table. So V table has some information in it, like it has, I think the size, it has alignment, it has a drop function for it, and it has like any trait methods on it also. So I think this first one, size, alignment, and drop function, I think is where the 3 comes from. And I think it just doesn't really matter if you have more entries in it for other methods in the V table. So anyway, that's a layout for that. Tells the compiler how to represent things. Then this ends up affecting like codegen and everything else kind of further down, like what types get passed to LLVM and all that. So yeah, so that's Dyne star. I wonder what the other, curious what this other like fix me is. We just have one there, but oh yeah, here's the yeah, this is, I think, saying what I was just saying, but probably better and more accurately. Anyway, I guess 2 people have gotten in trouble with this so far. So yeah, that's the way we represent a V table pointer in there, because otherwise it ends up being pretty tricky. Oh, okay, cool. Michael added a link to the where we say that Dyne star trait implements trait. So I'll go ahead and pull that up on here too for completeness. So here. I'm looking to see if we have like a real obvious like Dinestar reference.
It's not Dinestar specific. This is just how all auto traits, or sorry, all din or dinstar implements its own trait.
Okay. Cool. Oh yeah. They're dynamic implements, right? Because din trait implements the trait, but I don't think box din trait does, right? Like that ends up working through the deref trait.
Correct. Unless box din trait implements the trait through an impl block. So for
Right, okay.
example, a box of din future implements future, not because of din. It's just there's an impl for future for box of din future. Same thing with
Okay.
mutable references to din future.
Okay, cool. Thanks. Yeah. Yeah, so that's something that's different between like boxed in future and Dinestar future is Dinestar future and just automatically implements future, and Dinestar any other trait automatically implements it. Whereas you don't really get that for free when you have a pointer around it. But anyway, so here we have this tie dynamic, and we basically go through the traits that are, you know, I think that's in the principle and all that. So this is where we say here are the traits that a design trait object implements. So cool. Okay, so one of the things I wanted to point out about the next step, which is sort of the mirror lowering and monomorphization and all that. There's not a lot that actually needs done as far as like mirror lowering goes. But one thing we did need to do is make sure that like any of the methods that go in a dinstar v table get like monomorphized, or you get monomorphized instances of all of those. And so it ended up being pretty simple. We just add this extra clause to the part that's, you know, visiting all the R values. And we say, hey, if we have a dinstar object, make sure to visit that also for vtable methods. But that was needed to keep from getting link errors and things for when we, because of those, we'd have missing destructors and so on. So that's that. Let's talk about the actual like code gen parts now. So I'm going to talk about 3 different parts in this sort of coercion, which is where you go from a thing into a Dinestar. Then we'll talk about method calls, which is doing something with that, and then dropping, which is like you're done with the Dinestar, and so you need to drop it. And each of these took a little bit of care to make that happen. So basically, I should have added the vtable code also, the one that finds the vtable. That was something that ended up working just sort of for free. The way that we get vtables already, it's just now we're getting the vtable for like, you know, like if you have box of future instead of like, so a box of din future is it's like a wide pointer with a pointer to the future, and then also the vtable for that thing as a future. And what we ended up storing here, when you have box of din future as a dinstar, you end up storing like the vtable for the box of din future rather than just the din future itself. And then everything just sort of works. Like it gets that generates the right drop glue that calls the destructor for a drop or for box, and which then goes and calls the underlying feature and so on. So that was kind of cool that just worked out. But anyway, here's how if we're casting a like an R value into a dinstar, we take the value, we get its data and its extra information. Yeah, so we pop that out. Oh, and then we call this cast a Dinestar on it, which is actually probably where the real work happens. But we end up with a pair of this LL data and LL extra, which I think is just the data pointer and then the vtable part of it. So let's go in the cast a Dinestar and see what that looks like. Yeah, so some checking to make sure it's all correct and all that. Yeah, so we had to do some special, like, see if it's a pointer or not, because depending on whether it's a pointer, we either do a bit cast or a pointer to int cast. But we take the underlying type, cast it into a usize essentially, and then return that here. So that's what the source field is. And then unsized info is this. Okay, so I think this unsized info is the part that goes and finds. Yeah, so we have dynamic. That says it's a no-op. Trade up casting coercion. Yeah, here's the part where we get the like the vtable pointer type. It's LO vtable pointer cast. Oh, right. Because there's the vtable for a type is just a static table. So this is, we say, here's the type, give me the vtable for that. And then we can, return that. So we're sharing a lot of code with the existing dynamic casting stuff. Yeah, I don't think there's anything particularly special here about DenStar. It just kind of works, which is cool that it shares a lot of the same implementation. Okay. So that's coercion. Next up is method calls. So it happens in block.rs. And oh, it was 948, which is where it already was. So basically we added a, so this is the call terminator, which can be for a method call. And we added, before everything was always like a reference or a pair. But yeah, pair is like for, I guess, for RC self. Yeah, RC self methods. So we added a new one for immediates, which is the way that DynStar ends up showing up through here. So for this, we basically load out the we load the operand to it. We get the first and second field. The first field's the data pointer. The second one's the metadata, basically the vtable. We pull the method out of the vtable. Yeah. Oh yeah, ADX. That's our index that we're calling for the method we're calling. Yeah, so we get that, we set up our arguments, and then we continue. So yeah, basically just pretty similar to an existing like vtable. I guess that's what this is doing. Yeah. Okay. So it's a little different because we're going through like kind of one extra layer of indirection. So we have like a reference to a DynStar rather than just the DynStar directly, which is why we need to have this extra load and project out of it. But otherwise it's, you have LFN and largs.push, which is basically what we're doing here in the existing dynamic dispatch case. Okay, so that's method calls. And then earlier in the same file, we have the drop glue. So this ends up looking kind of similar to, here's the existing like dynamic case. And then we have this new one for DynStar, which is very similar, but I think kind of, again, it's because we're going through these extra layers of indirection. We have to do that. So this is kind of like we did before. We get the data type for it. We get the vtable pointer by looking at the second field. Then we load that to get like we load out of that second field to get the vtable, and then do a basically a method call to drop. So I guess drop in place is like a well-known vtable entry. So we pull that out, and then we anyway, that gives us that's how we get to the destructor. So it's the same way we did for method calls. We load out the vtable, and then we read the right index for the destructor, and then we sort of pass that up to the calling code, and then that goes and generates the rest of the destructor call, just the way that any other type we get dropped. So does that make sense so far? It's going over it kind of fast, I think, but okay, cool. Anyway, so those are like kind of the main highlights of the code I wanted to point out. I don't know if anyone else has questions, other things they want to see, or things maybe I missed. You know, if there's anything else I should cover or go over, or if not, we can move on.
I have one. Maybe you covered this, I missed it, but are we synthesizing implementation methods for the den star type? Or are we somehow pointing to the original methods for the
I
impl
think
that?
we're basically, let's see how does this happen. So basically we ask there's like code that generates vtables where it's like, oh, I need a vtable for this trait, this type as this trait. And we do the same thing. So we'll have like the data field will be like, a box of T. And so we can say, hey, give me the vtable for box of T as trait. And that's the one that we store in the second word of it. And then we generate in the method code that we were just looking at, which I think is here. Yeah. So basically this is where we load out the two fields. We look up the vtable that we generated, and then that just kind of works from there. So we are making a vtable that didn't exist before. I'm pretty sure.
Right, but you can use the existing methods because your self type is pointer size. So it's, there's nothing, no magic that has to happen on the other side of the vtable. It's just,
right.
Okay.
Yeah. Yeah, that's how that works. Cool. Okay. Well, I think that's all. That's all I had then for the code walkthrough, and that's most of my content. I'll go ahead and pull the slides back up. There we go. Or not really slides, it's a document. I was going to make them slides to start with, and I just decided HackMD works just as well. So anyway, that's the code walkthrough, and then I'll add just a little bit of what's next. So first of all, there's a tracking issue here that so here's oh, sorry, I'm looking at the chat there too. Okay, cool. So here's some open issues. I think some of these may be fixed by now, or at least will be fixed shortly. But I'm going to plan on keeping this up to date as we go through, as we find new issues. So if you're interested in helping out, this is a good place to look. A lot of these are, because it's such a new feature, a lot of these are really simple, or are relatively simple as far as compiler bugs go, where it's like, oh, we've never considered trying to cast this thing into a den star and it broke because of some weird reason that we didn't see ahead of time, and it just needs kind of a special case, and then it will work. So anyway, that's a good place to start looking at for that. Michael, I see your hands up.
Yeah, I don't think any of these issues actually need to be fixed. I think there are open PRs for all of them, except for Rust format, which just needs to be bumped. Like someone from the Rust format team just needs to bump the in tree version of Rust format that we use. Just for the record, I don't want anyone to start looking through this issue and start fixing something that's already fixed.
Okay. Yeah. Thanks for sharing that. I knew we were like, I knew your changes had addressed a lot of these. I just wasn't sure if it got all of them or just like most of them. But anyway, these are currently it sounds like pretty much all fixed or will be soon. But I will continue to update this as we find more bugs with DenStar, and I'm sure there will be more. So there's that. And then also the other kind of big question is these conversion traits. So right now, so here's a link to another document I have. We talked about this, I guess, about a month ago. It seems longer than that. But we want to add some traits to do that sort of help facilitate this conversion into and out of a DenStar. And sorry, I was getting distracted by the chat again. Anyway, so we want to have some convergent traits in there, and that does a few things. It lets oh, that's a typo there. Let's fix that. Um, yeah, so we can do some. Basically, what this says is like what things can be converted into a den star and how that happens. And there's a lot of kind of open design space around this. So we're gonna anyway, hopefully soon we'll get this like kind of finalized and get something we can start experimenting with. And I think that'll unblock a lot of additional work on DenStar. But these conversion traits can help with things like right now there's some questions about like when we need to do indirection or not. There's a kind of a small value optimization you can do where if like the thing that you're casting into a den star is like a U size, you can just store the U size in the object itself rather than having to have a pointer to it. But then if we're not careful, that ends up penalizing all the times that you actually put a pointer in there and so on. So those are kind of the questions we're wrestling with that. I would recommend if you're interested in that, like this document that I've got up on my screen is a good one to read. And you know, how we're having discussions in the WG async and the WG async slash async functions and traits Zulip channels. So those are good places to look for that. And anyway, that's kind of what's going on now. And then, okay, so then my closing thing was just a bunch of contact information for me with, it looks better if I put it in the view thing. So here we go. Now you can see all my little images that I've stuck in there. Anyway, so thank you for listening and thanks for questions. That's all the material I had. I can stay around and chat about anything people want to talk for another half hour or so. I have a bunch of ways to contact me there. You can email me. You can, I guess you can't really message people on GitHub, but you can see what I do on GitHub there, or you can reach out to me on Twitter, or I guess a lot of people are Mastodon now too, or have been moving there. So I'm also hanging out there. And then I linked a blog post of mine that I wrote a while ago that I think kind of has it's from a few months ago, so it's somewhat out of date, but it is an overview of a lot of the things that I talked about in this talk as well. So, and if you find that helpful, that's worth looking at also. So anyway, thanks. Anyone have any questions or anything?
Just a small one. And thanks for the presentation. It was very nice.
Thanks.
I noticed like some fix me's in the code you walk through.
Yeah.
Are there any of those that make sense to like go through and have a crack at, I guess?
Yeah, let me thanks for noticing those. Yeah, a lot of those are just kind of, you know, again, because this is very new code in the compiler. A lot of these is very like are very like, you know, oh, we just didn't get the chance to implement that. There, I think, won't have a lot of really deep questions about like, you know, oh, what's the semantics of this and how does this interact with this feature or that feature? A lot of it's just kind of like adding in some extra, filling in some missing cases and things like that. So yeah, I think if this is an area you want to help out with, the grepping for fix me DynStar will give you a lot of good places to start out too. So cool. I think I saw another hand down below, but now it seems to be gone. Okay, I guess there was not another hand there.
Are these HackMD documents like collected somewhere? If you wanted like an overview of the documents related to this topic, or is that not a thing?
I think they are not very well collected, unfortunately. I that's something I've been wondering about is like I think there should be a better way to do, like HackMDs are great for sharing a doc and working on it together and stuff, but I don't think we figured out a good way to like archive all of the, like we'll do meeting notes a lot of times in a HackMD and I don't think we have a good way of archiving those and making them discoverable. I don't know, maybe we could put it on the async website, the WG async website, and just say like here's documents we've made.
Eric, these hackathons are in your personal account, or because like maybe you have seen that there are some teams like there is a Rust traits team, or there are a couple of teams related to that where we put a lot of documents. But I'm not sure if these ones are in your personal account, or if even is there is an async team or something like that in there.
Yeah, we do have an async team. This particular document I put under my personal one, but I can move it into the async team. While I was working on it, I was like, oh, I don't want it to be like, I mean, not that anyone ever looks at it, but I was just like, want to keep it like private until I get it ready to share. But now that I've presented it, I can move it into the async team.
Yeah, but maybe you could have a folder or a tag within that, or you could just have a doc with links to DINSTAR stuff and like keep that one up to date. That's kind of like a start. Whatever works.
Actually, that'd be maybe in the tracking issue, that'd be a good place to put like maybe in addition to like open issues, also say like links to documentation. That'd be a good idea.
That would work.
Yeah. Maybe I'll do that. I'll try and collect some of the DINSTAR docs that we have and put it there. Cool.
Nice. I think it worked really well, like presenting from the HackMD. That was very nice, like live coding and stuff.
Awesome. Yeah. I was originally going to make like a, a full like slide deck and stuff. And then I was just like, actually, I think HackMD works pretty well. So
yeah, that was good.
And then at the end of it, we have a document we can share, which is also kind of nice.
Gonna probably stop recording. So we can keep chatting, like unless there's any other question or something specific to. Yeah, probably. I can edit it anyway, video, but